Welcome back, and we will continue with the program, with the second half. And we have two more speakers and a panelist and an awards ceremony. So we have a lot of things to do. As I mentioned before, hydrogen is often seen as a good zero-emission alternative to traditional fuels. There are a lot of challenges, but the question is, how can we implement that safe and efficiently? We have here Volker Baumbach, Manager Aerospace Engineering from the Airbus Group, and he will tell us more. So I would say, give a big applause for Volker.
Thank you very much. Hopefully you can hear me, and the mic is working brilliantly, thanks. And it's an honor to be here and to speaking to these students today. And I was like a little bit rephrasing my introduction 3 times because my slides have already been shown. So nevertheless, I think global warming and carbon dioxide is the point we discuss here, and meaning refueling, fueling, and the right fuel to have in place. And we talk a lot about it, but is talking just enough? Is my question. So we need to turn something, we need to change something, but is change enough? I don't think so. It is the transformation we have in front of us. It's the transformation of the aerospace industry. And this is also an opportunity, I believe, because there's a purpose. There's a purpose behind to make it sure that the next generations, in the next 10, 50, even more years, can survive on this planet. And there's even the engagement which is in there. And this is what I'm trying to show you in the next slides, where I believe that all these students here are necessary to make this transformation happening. So, what do I have? Don't be surprised if you see the attack chart again. So this tells the story, principally, where we have to be in 2050. The 1.5 degrees of the Paris Agreement needs to be fulfilled. So different options we have. If we do nothing, we follow the red line. If we do have the right technology, and we have proven to have the right technology. There is the A320neo, there is the A320 XLR, there is long range, and we have done a huge vast of investment into the new engines, which do actually save the fuel today. You can't change just simply a wing and make it more efficient, but the engine can be replaced. We have talked already about it, sustainable alternative fuels. Is the majority of the chart you can fulfill. There is also operation infrastructure, artificial intelligence. How do we do the flight management system? There's a huge amount of improvement necessary and possible. This is the good thing in it, necessary and possible. So I'm a little bit more talking about the hydrogen, which will be the next few slides. And I was thinking, those are the students having the thermodynamics, having the fluid dynamics, and I want to tease you later a little bit. And the question is, what is the Airbus trajectory? Airbus trajectory, we have seen this slide, so I quickly go through it already. There's the NEO launch, the CRE launch in 2019. Yeah? We will have the possibility, hopefully, to fly 100% of sustainable alternative fuels by 2030, and in 2035, the expectation is to have a new aircraft in place, and we are working hardly on it. However, we have 7 years of development, and this is what we do now, is a pre-development. We try to make the bricks together, that we can run the right development in time. However, in 2050, we should have a fleet which supports the idea of the 1.5 degree Paris Agreement to be carbon dioxide neutral. So what does it need for being sustainable? It needs hydrogen. Hydrogen, we have spoken about it today. the weight in terms of unit energy. You have 3 times the weight of kerosene in comparison 1 times the weight of hydrogen. The volume is a bit tricky because it's 4 times more than kerosene. So you need to have a look what weight means. So we have to have weight in focus. We need to have larger volume requirements, right? So where do we put the hydrogen? Because it's a huge tank in that aircraft. Volume versus range. So we have talked about this already. Where do we put it? Is it 1,000 nautical miles? Is it 2,000 nautical miles? Do we need to have a fuel cell? Do we need to have a combustion engine? All these questions are principally on this matter of physical facts. So the options we have are principally mentioned already today, is H2-burn aircraft, so pretty much 2,000 nautical miles, and Thomas has already spoken about it. I don't need to go into the details because we know this is currently an engine which is standard type of technology, burns at a different temperature. We have still the NOx problem. We still have the hydrogen, the contrails problem, and this is not gonna just away. So we have to put more research in it, and this is gonna be done together. So we're working in projects and make sure that the demonstrator is flown in 2018 somewhere, and to make sure that we understand the physics beyond new engines, different fuel, and the contrails. What else do we have? We have fuel cells. Fuel cells have a different measure of putting the thrust onto the aircraft. We use electricity, so we have classical oxygen from the air, we have hydrogen from the tank, and we produce water. It does not diminish any of the contrails, but the carbon dioxide is no longer there, okay? So, and just to mention it, there's a simply bit better of efficiency for the fuel cells. So, how does it look like on an aircraft? And this video has been shown, and I've got the full video, not just the picture, because I've got access to it. The part is, Airbus wants to understand how this is going to be specified. So for the demonstrator, Airbus is extremely willing to put the engine powertrain together on its own to make sure that we've pretty well understood from end to end how such a thing needs to be specified. This was the polished part of the presentation. So now we're going to go a bit into the details. What do we really miss in terms of getting hydrogen on an aircraft? And I think this is, just in a couple of words, a whole story behind getting hydrogen into service, because regulatory is one of things. Standards, refuel standards. How do we manufacture? What is the quality of hydrogen? Where do we get the hydrogen from? How do we transport it? What is the infrastructure? Just as an example, Schiphol is very densely around everything, so we have a lot of cubic meters of kerosene, and all of a sudden you want to put hydrogen in it. Where do you store it? I told you it's 4 times the volume, cryogenic, minus 250 degrees. So where to store it? And we need to make sure that we don't boil that much of the hydrogen off, because hydrogen has a secondary impact on the global warming. Yeah? So all these kind of things are not sure today. We need to manage it. There is cost. We spoke about cost. Sure, is cost a problem? So this is why we have a European strategy. We have governmental strategies. We go abroad. We try to buy and make sure that we've got enough of the hydrogen in future to fly with it. Technology capability, and we spoke about this in the panel, because there's one thing. Capability means, or compatibility means, safety. We need to make sure that we've got an aircraft which gets to be refueled in 20 minutes. We need to have a safe aircraft, because we need to generate trust. You need to go and feel safe. You need to put your seat back, close your eyes, and make sure you're going to land safely. And this is trust, and this is technology compatibility. So, what do we need? There are a couple of requirements we need to fulfill. I just told you boil off. When we store the hydrogen on the aircraft, we expect to have the aircraft without any boil off for more than 10 hours. We don't want to chill down the system every single day, so we expect the system to be chilled down at a temperature to minus 250 degrees for 5 to 10 years. So you don't want to release any vacuum on the system. And this is just to give you an idea. So you need a tank, which is a double vessel, inner, outer cell. In between, you have vacuum to make sure you have as less as possible heat ingress into the system, not to boil off the whole hydrogen. And you need to have probably multi-layer insulation. So this is, just to summarize where we are, this is a difficult topic to make sure that the vacuum stays for more than several years, up to 10 years maybe. Okay? On top of that, I was talking about different options. So here we come a little bit into the physics, so to tease a little bit the students. This is one example. If you fly a fuel cell and you have the tank in the middle, which is a storage, there's a heat exchanger to keep the pressure. You have a vent system, you have a refuel system, which is all systems which makes it complex. However, you can distribute the hydrogen directly to the consumer with just exchanging the heat and make it and provide it in the terms of a vapor. Okay? So on the right side, you see the PT diagram, the phase diagram. So you can operate the tank at equilibrium conditions. So that means basically you fly with a boiling liquid. So far, so easy. Okay? If you have a longer range, you need to provide more hydrogen to the engines. So we come back to the combustion. It looks a little bit different. On the left-hand side, pretty much the same thing. Storage, vent, refuel, and you need pumps. Cryogenic pumps. Just to give you an example, today pumps we have in space on rockets, they last 300 hours, and 300 hours is simply not possible. We need pumps which last 25,000 hours, 50,000 hours on the aircraft. But this is not the problem here. The problem here is, imagine you run it at equilibrium conditions, and you have a boiling liquid, and the liquid comes to the pump through the suction line and cavitates. Cavitation is a problem and might become such a big problem that the whole conditioning system chokes, so which ends up in an engine flameout. So we need to make sure that these physical things are understood. This is why I put it a little bit differently. So you see the dot on the right-hand side moves a little bit, right? So we tried to operate it subcooled. Subcooled has a different challenge, and this is where the devil and the detail have a contract. Yeah? Because this does a different thing in the tank, and this we will see on the next slide. On the video you see just a tanker which is taken from YouTube, and the tanker deaccelerates and it sloshes. So imagine the following thing. On the fluid you have cold temperature, in the gas phase you've got a very warm temperature, and all of a sudden they mix up, recondensate, and the pressure drops. And we need to really understand how the pressure drops, under which condition the pressure drops. And this is a simple example here because it's just one vector direction of the deceleration. On an aircraft, it's completely different. Imagine you have cabin depressurization. You need to have a rapid descent. Just as an example, multiple accelerations. And we don't know what happens on the aircraft, but we need to anticipate what happens. And there's a whole lot of physical problems we have to make sure we understand before we go into a design of an aircraft. Okay? So, what else is, this is how a typical storage looks like. Just let me go quickly through it. You have a tank The tank has a vacuum inside. You have gas heat extraction for the vent system. You have level probes because you need to make sure that the pilot knows exactly how much mass of fuel is on board. And this needs to be quite accurate, to be honest. And this is a difficult thing if you think about the 250 degrees Celsius. Yeah? So these sort of technologies need to be developed now to be in place in 2028. Okay, why I'm talking about these things is because we have to crack this contract between the devil and the detail. And this is why we need clever and intelligent students to be ready making this happening. Okay? Oops, it's a bit too far. So because just as a summary, there you see the QR code. You can directly go to our web page. You can find open positions in ZERO-E, in hydrogen, in whatever you want to do, propulsion engineering, cryo-engineering, structural engineering. And if you see these kind of things, physics, thermodynamics, material science, this is the key. This is the hard wiring. The soft wiring is something different. How do we want to solve the problems? How do we want to cooperate in the future? How do we want to make things happening? Are we team players? Are we willing to do it? Is it here that we need to change and have the transformation? This is the important thing, and this is what I'm really asking to get trained for. Be in a team, work together, know what interfaces means, and do something together as you guys do for the TUDelft. This is extremely well education. Okay? So, my message here is we need the engineers in future, and if we go for a program, I think a couple of thousand engineers will be needed. And welcome on board. Thank you. Time is gone.
Yeah, you did a great job. Thank you for your presentation. Are there already volunteers, maybe?
I have to say one thing. I brought a couple of colleagues with me. Thierry, who is our guy who does architecture. Anna is doing simulation. And we've got even HR with us, Marlene. And you are all invited to talk to us because I think we need to have less distance between internet and getting into interviews and such kind of things, and come and see us. You're very, very invited. And Liam is with us as well. It's your last day, and thank you very much for your time spending from TU Delft in Hamburg. It's been a pleasure. Thank you.
Thank you, Volker. Are there any questions?
Questions? Yeah.
At the end of the day, thank you for your presentation. I think it was very good to go into some depths. We need that, and we have to see where the problems are. At the end of the day, it's about direct operating cost. When you want to make a new aircraft, I always learned it has to be 15% less in direct operating cost to bring a new program on the table. Now, you showed that there are many problems in getting the hydrogen, getting it on the location where you have to generate it, transport it. Can you say something about what the direct operating cost advantage would be to go to such a new aircraft for the same range in passenger kilometers as, because that's another thing that's played with. If you take a present-day A350 and you start using it, it's on 1,500 kilometers range in Europe, is maybe not the best way of doing it. With the hydrogen aircraft, you're looking at getting it right with respect to the design range. But coming back to direct operating cost, can you say something about that?
To answer your question directly, no. However, we all know it's three parts mainly. It's crew cost, purchase cost, and fuel cost. So you can make a decision where you save the money, direct operating cost. However, I believe if we design an aircraft today, it's not a measure of how much direct operating cost I'm saving at the moment I put the aircraft in place. It is more, what do I expect from the aircraft? Because we have a learning curve. Imagine the A320 has a learning curve of 40 years now. and how efficient this aircraft has become. Yeah? And this is the question. The question is not how the operating cost is today. Sure, we will offer something and we will talk to our customers in future, but I can't tell you what the costs are today because we are in a pre-development phase. We are struggling with other problems. We're just trying to make the technology and the compatibility right in place. But there is a point at the time where we have to pull the lever and say, this is where we start the development. And then we need the engineers.
Okay, thank you.
Yes, you mentioned that with cryogenic pumps, reliability is a big issue as well as cavitation. However, I think in the past year, the transport of liquefied natural gas has exploded quite a bit, and they also use cryogenic pumps. So what is the difference maybe that we can't use their reliable pumps, but what can we learn from them as well?
We can learn a lot. We can study how severe cavitation is, because the density between the fluid and the gas is not that much. So cavitation is simply the implosion of the impeller. However, I believe if you compare an industrial pump to an aviation pump, there's miles in between of weight. So my expectation for a 10 kilowatt pump would be maximum 6 to 7 kilograms, including the power electronics. An industrial pump, 50 kilograms.
Yeah, that's clear. Thank you
so
for your answer.
there's a lot in between, and we have to get this down.
Yeah, thank you.
Also, thanks for your presentation. You're putting the finger on the real issues, I think. Now, if you look around Airbus, you'll find out that there's a lot of experience in the company, because for space, we've dealt with some of those issues for decades in building rockets, LOX hydrogen rockets, so the handling, the insulation, the slosh baffles, which we've developed against sloshing, etc., etc. There's lots of stuff there. To what extent are you using it? Taking another example, hydrogen pumps, we've developed them over decades as well, not to the safety requirements of aircraft, quite obviously, and not to the life duration of aircraft either, but there is technology, there is solutions on which you can take up.
Yeah.
To what extent are you doing that across the rocket experts, which you have a lot of in Airbus?
Thank you for raising this point. To any extent, there is a lot of information exchanging between Ariane Group, with Defense and Space. All these guys are on board. They join the team. We're hiring even people from there. But we need to be careful, and this is another message maybe. If you do the same thing as the rocket guys do, we don't fly on a rocket. Certification is a different story. We need to understand that. And this is why I believe we need to marry the space industry, the cryogenic industry with the aviation industry. And this creates a different setup of students, a different setup of capabilities and knowledge to be ready in 2028. Today, it's us who do educate the engineers, because we don't have them. But you're fully right, but we have to improve the cooperation between the two industries much more. But to be careful not to design a rocket. It's still an aircraft.
First of all, once again, thank you for your very inspiring question. Presentation. I have a question.
Give it a go.
My question is, we're seeing that Airbus has quite an ambitious planning to have this very disruptive technology implemented. How do you plan to assure the quality and the safety of this new technology?
How do you, sorry?
How do you intend to ensure the quality and safety of these new technologies? How do you verify the new system you're developing?
This is why we typically have a pre-development phase. So you have processes in place to design a kerosene type of aircraft, where the fuel is in the wing, most probably. And now we have different things. We have a storage in the back of the aircraft or somewhere else. So we need to make sure that we understand the processes of tomorrow, today, to make this happening. I think this is, and we need to engage with the authorities. You need to make sure. I don't know whether you guys know what common research, a review item is with the authorities. We have to open them. They have to understand how a cryogenic system works to make a safe flight happening, right? But this is communication. And communication, again, I mean, this is where we are. Communication is key. How do we communicate? What do we communicate at what time? So it's not just to pull the lever and make it happen in 2028. Right? We need to make sure that we have the brakes. A couple of things will be open. Lifetime of a pump. Don't care. We will do it, I'm sure. But does the authority understand what we are doing? And can we make the point that we can have a safe aircraft? So it's not pace. From my perspective, it's not speed. Speed is secondary. Yeah? First is safety. This is the measure. And we won't put a badge, Airbus badge, on an aircraft which is not safe.
Thank you.
I will go to the last question because we are running out of time. So,
Hi. Does Airbus plan to continue developing sustainable aviation fuel aircraft alongside the hydrogen aircraft that you're currently developing? Or is the A350 the end of sustainable aviation fuel aircraft for Airbus?
I think sustainable aviation fuel goes along with the aircraft we have in place. So you need to make a conversion of an aircraft. You need to make sure that the system currently in place is capable of consuming these sustainable aircraft fuels, right? So it's not just to make a new aircraft for a sustainable fuel, right?
Well,
maybe I got your question.
I meant both sustainable aviation fuel and kerosene alongside. Is there plans for Airbus to continue to develop what we could say is old technology with kerosene, or is the future totally hydrogen and there will be no new models of aircraft that pop up after the A350 that will still use kerosene?
I can't look that far in the future. However, I believe that kerosene is still on board and you need to have sustainable alternative fuels, power to liquid, something like that, right? However, I think there's a limit for hydrogen, if this is the question, and this is the trade you have to do. What is the power ratio of a tank, the storage? The storage is key. Storage is key. You need to have a selection of the pressure, you need to know what sloshing does, you need to know what the pumps are doing, and this is key. If you've understood that, you can extend the range maybe to 500 nautical miles, maybe 2,000 nautical miles. I have no idea. We need to do it now to make this as a perspective.
Okay, thank you.
Anything else?
one last question.
One last one.
Yeah.
Thank you for sketching the situation at Airbus. I guess you're doing good work. What about the competition in the world? What about Boeing,
I'm
China?
not sure Boeing is here, so you can ask them. So.
Well, let's hear it then. China, what's happening worldwide? Are you on par with the others, you think?
Well, I can say now that you're running out of time, but... oh, sorry. Go ahead.
Sure. I mean, we would be crazy not knowing what the competition does. But this leads us to what we do. Hope this helps.
I'm not the wiser.
Let's talk privately. So.
Well, Volker, I want to thank you for your presentation.
Thank you very much.
Thank you very much.